Okay, today taking a look at fractions, and we're going to do this over the course of a couple of days. So this is called Fractions Day 1. And we're going to start out by talking about what equivalent fractions are. So equivalent fractions are fractions that are perfectly equal to one another. And what we'd like to do, given two fractions, is to decide whether or not they're equivalent. And I'd like to show you three different ways that we can show whether the fractions are equivalent. And then after I show you all three of them, it doesn't matter to me which one you use. Just pick which one you like the best. Okay? So the first way that we're going to examine is going to be to reduce both, as in both fractions, to simplest form. And compare. And we'll do an example. We're going to do the same example for all of these. We're going to do 6 over 8 and 12 over 20. So we're going to take one at a time, and we're going to make them into their simplest form. So simplest form means they don't have anything in common on the top or on the bottom to one another. So if we take 6 over 8, what can I reduce both the top and the bottom by in this fraction? 2. So I can divide them both by 2, and what will I get?
3 over 4.
3 over 4. Is that in simplest form? Yeah, it is. So once I'm in simplest form for the first fraction, I'll move on to the second fraction and do the same. 12 over 20. What can I divide both of these by? 4 will work. Now, if you're looking at this and you're like, oh, I didn't see 4, I just saw the 2, that's fine. Just do it by 2, and you'll notice when we get to the end of dividing by 2, you could do it again. So since I saw some motionings for dividing by 4, we will. 12 divided by 4 is 3, and then the 20 gives me 5. So the two fractions that we're actually comparing right here now are 3 over 4 and 3 over 5, and what can you tell me about them? Yeah, they're in their simplest form, and they're not the same, right? They're different. So since the 3 over 4 that we got is clearly not equal to 3 over 5, what that tells us is that the 6 over 8, we'll put a word between them. Thus, 6 over 8 does not equal 12 over 20. Is that okay? So simplest form is one option. I kind of like simplest form. Obviously, if the fractions were larger numbers involved in them, that might not be your best go-to option. You might not like that very much, but it's not too bad. Another option is to get a common denominator. So common denominator for these two, just a general common denominator, would actually come about from just multiplying the two denominators together. So I have 6 over 8, I have 12 over 20, and I would multiply the first one by 20 over 20, the second one by 8 over 8. So in the first one, if I multiply 6 times 20, I get don't everybody talk at once. Thank you, 120. The sooner y'all give me an answer, the sooner we move to the next problem. Okay, that's where it goes. How about 8 times 20? Yeah, 160. The denominator is going to be the same for the other one, right? 12 over 20. So I'm going to get the same 160 on bottom because I designed it to be so. How about 12 times 8? Does anybody know that one?
96.
It is 96, yeah. If you memorize your 12 tables, you might actually still remember that one. We didn't do that when I was a kid. We only went up through tens, so it's kind of interesting. Yeah. Okay, these aren't the same, right? Just like before, they're in some kind of a form where we can compare them now. The denominators, they match, and since the denominators match and the numerators don't, the fractions are still not equal. So 120 over 160 does not equal 96 over 160. So again, 6 over 8 does not equal 12 over 20. Okay, we're going to get the same result every time, just from a different perspective. There's one more. This is getting a least common denominator. So we'll call it an LCD. Least common denominator means the smallest denominator that they have in common. So in particular, if I'm looking at 6 over 8 and I'm looking at 12 over 20, I want to know the first multiple that the denominators have in common. Clearly, I can go all the way up to 160, but it's a little bit overkill. What number in multiple, like if you list out the multiples, is the first one in which they coincide? 40. And so if you recognize that one and you like this method, it means the first one gets multiplied by 5 over 5, and the second one gets multiplied by 2 over 2. So 6 times 5 is 30 over 40. So 30 over 40 is one of my fractions. The other one is also over 40, but what's the numerator? 24. And 24 over 40 does not equal 30 over 40, right? So 30 over 40 does not equal 24 over 40. So 6/8 does not equal 12/20. Well, I don't have it in my notes. There is one other way that we can compare these. So I think I'm going to go ahead and throw it in here since I'm at this point anyway, even though that's not in your notes. So we talked about this one in a different class I'm teaching just, I don't know if it was Wednesday, or I think it was yesterday, or maybe Monday. I don't know. And this way is actually, we'll call it, let me move to the end so I have a space. We'll call it number 4. So the fourth option. So I have 6 over 8. And I'm trying to decide if it's equal to, so this is sort of like a question mark, 12 over 20. Another option that you can do is you can actually cross multiply. So you can take a look at 6 times 20, and you can take a look at 8 times 12. So you just cross along the diagonals. This is the 120 we saw just a moment ago, and this is the 96. If they're equal at this point, the original fractions were equal. If they're not equal, then the original fractions were not equal. So this is not equal, which means the 6 over 8 does not equal 12 over 20. It's a little bit more hidden in the background of like why it works, but it still is another method for determining if the two fractions are equivalent. Okay, so now that I've shown you 4 ways, and not even 3, you just get to pick which one you like, use it for the problems you're doing just to make sure you're showing the work for it, okay? So what we're not doing is we're not turning them all into decimals and comparing them. That's not the point where we are in the class. We will talk about decimals, but right now we're comparing them in fractional form. All right. So we're going to take a look, what do we have next? At reducing, yeah. So reducing values. So we have reduced 36 over 1 over 2 to simplest form. So we've done a little bit of reducing so far, and what we're looking for is anything that they have in common. In particular, if we could see the biggest thing they have in common, that's helpful. But really anything will work that they have in common. So what do you notice that they both divide by? 2. That's a good place to start. So if I divide them both by 2, on the top I get 18, on the bottom what? 51. Okay, so they're not both divisible by 2 now, right? Are they divisible by anything else?
3.
Yeah, they are. And if you haven't, or if you don't haven't learned or don't remember, there's a trick for deciding if a number is divisible by 3. If you add the digits together, I know you probably know that 18 is divisible by 3, but bear with me for a moment. What is 18 if I add the 1 and the 8? What is 1 plus 8? 9. Is 9 divisible by 3? Therefore, 18 is as well. 51 works the same way. In fact, all numbers do. 51. What if you add the 5 and the 1 together?
6.
You get 6. Is 6 divisible by 3?
Yep.
So 51 will be as well. And you can do it with the original value, like the 102 at the beginning. Do you notice? 102, 1 plus 0 plus 2. Add them all 3 together, you get 3. Is 3 divisible by 3? Of course. So 102 would be as well. So that's a trick to check it out for 3s. It works for 9s just like that too, by the way. If it's divisible by 9, when you add the sum of the digits together, the number is divisible by 9. So on the top we have 6. What is 51 divided by 3? It is 17. So this is the reduced form for this fraction. Again, do you have to show all the steps in between the first part and the... No, but you got to show me something. You should not be able to jump from here to here. If you do jump from here to here, you're either doing your work on scratch paper and you really want to see it on your paper, or you're using a technique that your calculator has, which is kind of not the point. I mean, I don't care what your calculator can do. I want to know what you know how to do and understand, okay? So we don't want to do that. Go straight to there. Something in between. We can also create equivalent fractions by starting with a fraction, this one's 6/9, and having either a numerator or a denominator given. What we want to do is we want to take a look at how do we get from the 9 to the 27 using multiples. Like, what would I have to multiply 9 by to get 27? 3. So if I multiply 9 by 3 to get 27, I can do the same thing with 6. 6 times 3 would be 18. So 18 is actually the blank that I would be filling in using that idea. Okay? Okay, so when we multiply with fractions, there's two distinctly different, although somewhat overlapping, ways that we can multiply fractions. Option number 1 is that we simply multiply the numerators. Those are the numbers that are on top. And we multiply the denominators. And then the ending answer that we get from that multiplication across the top, across the bottom, we reduce it. There's nothing wrong with this method. It's very straightforward. It always works the same way. You multiply, you reduce, right? So in some sense, there's some niceness to it from that perspective. The not nice to it part is it often will create numbers that are larger than you really needed to work with along the way that you then have to reduce. So instead, if you would like to, you can do this one. We can reduce within fractions and across diagonals. And after we do the reducing, then we multiply numerators and we multiply denominators. Truth be told, the second one's the way I tend to do it. I want to keep the numbers as small as possible as I work my way through. I don't really want to reduce bigger values, so that's the way I tend to go. But we'll show it in a couple of ways, and then you can decide which one you like, and you can do it your way from there. So the example we're going to look at is 4/9 times 15/22. So if we do this using the first method, we simply multiply straight across the top. So what is 4 times 15? It is 60. And what is 9 times 22? That one's a little bit bigger. It's 198. Because that's step 1 and step 2. Multiply it across the top, multiply it across the bottom, and now we can reduce these. Now it's possible you get to this point and there's no reducing. This one there is. So 60 and 198 both will reduce. What will they both divide by? What? 2. We can do that, you bet. Both divide by 2. So if we divide by 2, I get 30 over what? You know what 198 divided by 2 is? It's 99, yeah. Will it reduce further? Yeah. It'll divide by 3, which would give us 10 on top and 33 on bottom. 10 and 33 do not have anything in common. 10's got only 2's and 5's it divides by, and 3 won't do that. So at that point, we're done. Okay, so that's method 1. Method number 2 does the following. It takes a look at the two diagonals. Well, it takes a look at the individual fractions, and it asks, is 4/9 in simplest form? Yes. Is 15/22 in simplest form? Yes. So you start with the individual fractions. They don't have to have been in simplest form to start, but these are. The next thing you do is you look along the diagonal, 4 and 22. Do 4 and 22 have any way that they can be reduced? 2. Yeah, they're both divisible by 2, so I can divide 4 by 2 and get 2. and 22 by 2 and get 11. And then I do the other diagonal. 9 and 15. Do they reduce?
Yep.
Yep, by 3. So 9 divided by 3 would be 3, and 15 divided by 3 would be 5. And once I've done all the reducing that I can, then I would multiply across the top. So 2 times 5 gives me my 10. And across the bottom, 3 times 11 gives me my 33. And if you reduced everything when you looked top to bottom and across diagonals, like before we did the multiplication, this will already be in reduced form when you're done. You should never have any other reducing to do at this point. If you do, you just reduce it and that's fine. But it just means that you didn't quite fully reduce the stuff to begin with if that happens. Okay? So I'd like for you to give number 2 a try. You don't need to do it 2 ways. Just pick your favorite way. Either do the multiplication and then the reducing, or do the reducing and then the multiplication. Once you have it in what you feel like is the final form that it should be in, just consult with somebody next to you. Make sure you got the same value as your final one. Okay, I saw a few of you consult with somebody. Everybody else do the same thing. Consult with somebody. Check somebody next to you. Just make sure you guys have the final answer the same. If you don't, see if there's a problem in somebody's paper. Did we find some mistakes?
Yeah.
Not a problem. Better now than later.
No.
No, okay. Okay, what did you get for your answer?
3 over 35.
3 over 35. So let me just show the reduced option and then go with that one. So this one right here, they have a 2 in common, so this becomes a 1 and a 5. This diagonal has a 3 in common, so I have a 7 and a 3. And if I multiply across the top, 1 times 3 is 3. Across the bottom, 7 times 5 is 35. Okay, so that's the second method on that one. Okay, everybody good with that? Excellent.
Yeah.
All right, third one. Number 3 looks a little bit different. It has a multiplication by a value of 4, right? So all I want you to remember is that how can I write 4 in fractional form?
4 over 1.
4 over 1. So as we work this problem, it's not any different than the ones we have done before. It just starts out looking different. And then all the strategies are the same. So on this one, if I do check the diagonals, there's nothing in common, actually. So either way, I end up multiplying across the top and multiplying across the bottom. And that's in reduced form. Now, can you leave it that way? You can. There's nothing wrong with that. If it super much bothers you and you absolutely cannot stand to leave it that way and you want to turn it into a mixed number, that's okay too. You can't turn it into a decimal though, because in particular on this one, there's no closed form of the decimal. You end up with some repeating stuff going on. If you decided to take this and turn it into a mixed number, you'd do the 24 divided by 7. I think we talked about this last time, right? It would go in 3 times, giving me a remainder of 3. So your answer would be 3 from the top, and 3 is the remainder over 7. But I am perfectly happy for you to leave it as 24 over 7. Okay? All right, any questions on that? Okay. Reciprocal. Do you remember what the word reciprocal means? Do you have a question? Sorry. If the question starts out with mixed numbers in it to begin with, the answer should have mixed numbers. That didn't actually happen here. Like we had a whole number and we had a fractional piece. So there's no like inclination that says I should put this back into mixed number form because it didn't start that way. Yeah. And we will have cases where it will simply say find the mixed number for this too. That'll happen too sometimes. Okay, do you guys remember what the reciprocal is? Yeah.
Isn't it like it flipped around?
Yeah, so that's how we think about it a lot of times. It just flips fractions upside down. Okay? So definitionally, it is the multiplicative inverse of a value. So multiplicative inverse simply means if I were to take a value and I flipped it upside down and I multiplied it by the original value, I'd get back 1. It's the inverse. It undoes a value. So if I have 4 over 7, what would 4 over 7 be the reciprocal of? 7 over 4. And the y part is really because 4 over 7 times 7 over 4 equals what? 1. Okay. Okay, so the reciprocal, the flip of the fraction, those kind of an idea. How about 3? What is 3 the reciprocal of?
1 over 3.
Yeah, 1 over 3. So if you were looking at that and you were like, well, how do I do the reciprocal? There's no way to flip it. Remember again, 3 is the same as 3 over 1. All right? So I can flip it, and I will create the fraction 1/3. And why does it work? Well, it works because 3 times 1/3 is 1. It's always the reason why. So how about 3/5? What is it the reciprocal of?
5 over 3.
5 over 3. And the reason why? Same thing, yeah. Because 3/5 times 5/3 is equal to 1. That's the why. Okay, that's going back to the definition. Okay, the last thing we're going to take a look at is division. So you might be thinking to yourself, we started with fractions today, and we started with multiplication and division. Why did we do that instead of addition and subtraction? And the answer is because it's a lot easier to multiply and divide fractions than it is to add and subtract them. So we started with the multiplication and division. So division is actually the inverse of multiplication. So if we think of the fraction 8 divided by 4 as a fraction 8 over 4, we can also think of that as 8 times 1/4. So these are all 3 equivalent ways of writing the same quantity. So when we take the number 4 and we use it as division, it becomes multiplication by the reciprocal of 4, which is 1/4. That's where that's coming from. Okay, it's not just like this cool trick that somebody said and you have to agree with. It really works, and it works from that concrete standpoint. So when we're looking at something like dividing 2/3 by 6, this is division. And we can turn it into multiplication by saying 2/3 times what?
6 over 1.
Okay, that's what it's already divided by, is 6 over 1. So what would it be multiplied by? 1 over 6, right. So notice we flipped the second fraction. That is the fraction that was 6 over 1, right? Because this basically says right now 2/3 divided by 6 over 1. We always flip the second fraction. Jot that down if it's something you think you might not remember. You always flip the second fraction when you're turning this into multiplication. But then it becomes a problem that we've already done several of today. We can reduce across the diagonals and so forth, or we can multiply across and reduce at the end. Just because I haven't done it in a while, let's multiply across and then reduce at the end. So if I multiply across the top, I get 2. How about across the bottom? 18. And then what will these both reduce by?
1 over 9.
Yeah, they'll reduce by 2 to give me 1 over 9. If you want to reduce before and then multiply, fabulous, no problem. So what will this change into for number 2? What equivalent multiplication statement?
3 over 10 by 4 over 3.
Okay, so 3 over 10 times, right?
Sorry, this one.
Yep, times 4 over 3. Is everybody good with that? Okay, let's reduce this one. So if I reduce along this diagonal, the 3 is actually reduced to 1. And if I reduce along this diagonal, they both divide by 2 to give me 2 and 5. Multiply across the top, I get 1 times 2 is 2. Across the bottom, 5 times 1 is 5. And it's in reduced form. Okay, any questions?